This is my presentation on natural language processing, and the figures here are BERT and ELMo, and they actually do come up. They are the names of some important things that have been developed by researchers. There's also Ernie, there's Albert, Robert. People in this field really like naming things very creatively. Anyway, one of the first things we're going to ask is, how will we communicate with our computer? And the first step is we speak to the computer, so we want to encode what we're saying as vectors, because computers will best understand numbers in vectors. And when we're considering this, we have to consider what each vector represents, what the distance between each vector represents, and how will we choose to do this? What method will be computationally fastest? What method will give me the most accuracy? How do I decide a benchmark for what is and isn't good, etc.? There's also then the concept of decoding, because we have to, if we want to get an output out of this, if we, let's say, set a problem where we generate predictive text, we can't just get a prediction in terms of the numbers. We now have to figure out what those numbers mean to people. What will we see? And here we need to know what each vector is representing. We need to know how each vector relates to what comes before it. And linked to this, we need to figure out if what we've just said makes any sense. So when it comes to encoding, first of all, I would like to make a distinction between us just representing each word as a dimension, which is one hot representation. That is very computationally expensive, and we don't really get much insight. Instead, we can use word embeddings, which are the types of things we'll focus on today. So things like BERT and ELMo, they're all word embeddings. With this is the concept of transfer learning. That is, every time we run our model, we're not going to sit there retraining it on the 4 words we've typed. We've already learned about various words. We've already got an existing embedding, and we're going to use transfer learning to adapt it to our purpose. So if all our words are going to be linked with a particular topic, if we're training a chatbot to deal with people going on lunches, we're going to transfer learn and make it understand our context better for our purpose. But we're not going to teach anything from scratch, because models such as Word2Vec, GloVe, and BERT, they've been trained on huge corpuses, a corpus being all the words it's been trained on. So BERT has been trained on, I think, several million words we've shown it. So it's going to work a lot better than retraining a model over 5 words every time we need to use it. And there's also another reason. So with transfer learning, we start with a higher initial performance. We also have a higher slope when we start learning. That is, our accuracy increases, and the rate at which it increases is greater if we use transfer learning, which then leads to a higher asymptote that we end up at. All reasons why transfer learning is perhaps the best approach with the use case of natural language processing. Another thing that we mentioned earlier was what the distance between each vector would mean. So usually we want to consider it to be semantically accurate. That is, for example, this common example of gendered words are usually the same distance apart from each other. Man is to woman what king is to queen, as many people would have done if they had to do 11+ exams, or if you ever had to learn about this at school. This is a very common concept. However, there are also other examples that often get dismissed, such as considering the relationship between a singular and a plural. And there is a paper. I will link all the papers. I'll send all the links to papers to the Archimedeans. They can add them when they finish the recording. But this paper is the first paper that was published linked with Word2Vec, how we can convert word to vectors, and how that automatically brings all these relations. The relations they tested were singular to plural, base word to a comparative to a superlative. So best is a superlative, better is the comparative, good would be the base. There's also other relations such as a possessive and a non-possessive, and there are links with tenses. So you can test the verb with the base, the third person, plural, the past. These are the tests that they chose. We now have other ways of testing them, but the main way we encode distance is just a simple cosine distance. This argmax thing is just saying that it's not your distance that you're getting, it's the argument that had the distance that you're getting, if that makes sense. It's the argmax part is just straight from the paper. The main thing that matters is you're measuring the cosine distance between any two vectors. And that's how you're deciding whether or not the relationships are being maintained. And there are benchmarks that they've increased from then. So initially, the benchmarks were set on certain semantic relations, such as these relations. However, we now also look for sentiment analysis benchmarks. We regularly test the models against them. When this original paper was written, they were very proud to have a 40% accuracy rate. 40% of the time, the relationships were preserved between a singular and plural amongst multiple words. Now we're looking at 80%. Now we've improved significantly. And I'll go through in the presentation on techniques that have led to these improvements. One of the big things that we use to encode these languages are a recurrent neural network. What is a recurrent neural network? Well, most people see feed-forward neural networks. That is, a layer 1 feeds forward to layer 2, which feeds forward to layer 3. Whereas a recurrent neural network has cycles. But you might be asking, is an RNN doing the same thing as backpropagation? I mean, backpropagation links the earlier layers to the oncoming layers. That's just not the case. Unfortunately, they're describing two entirely different entities. Backpropagation is a technique where weights will update backwards. So you will get an output. The output was incorrect by a certain margin, let's say. So your weights will update from your layers closest to the output all the way backwards in a way that would have led to the correct output. Whereas a recurrent neural network looks a lot more like this. Oh, and also, I should have mentioned this link. There are other alternatives to backpropagation that will be described on this OpenAI link. Apparently, certain things called evolution. However, I personally am not too sure how well they're coming along in the research, as the article that is linked there was made in 2017 saying it will be revolutionary. Since then, every model that I've seen has just used backpropagation. They haven't used other techniques. It hasn't caught on as well. However, backpropagation isn't necessarily the only way you could update your weights. It's the way that most people choose to update their weights. A recurrent neural network looks a lot more like this, where there's this cycle going on. If you unfold it out, let's say your cycle varies with your weights update with time. So if you've got sequential data, if you've got a word and then another word and then another word, it's very useful because the weights, the current way the cell is operating, your current layer, the way it's operating, is also dependent on the previous word. So you get some form of memory. You remember what's happened before and it affects the future actions. Unlike something like a convolutional neural network, which uses a feed-forward network and backpropagation. That is used in imaging, where what you've seen previously doesn't matter as much. It's not sequential data. So this is a recurrent neural network. The thing that makes it recurrent is the presence of these cycles. If instead of layer 1 affecting layer 2 affecting layer 3, we had layer 1 affects layer 2 affects layer 1 and layer 3, and then in the next pass, that way the layer 2 affected layer 1 will affect layer 2 again. It's a lot of use of the word layer. The layer is a real word. But that's how the cycles form, and that's what makes it a recurrent neural network. So we've done all this encoding in our network. We now have to decode. Decoding is actually a lot simpler. There are greedy algorithms, as we call them. We do a greedy search. So let's say we have a greedy search method. There's also a beam search method. You will soon find that beam search is just, in some way, like you say, a generalized greedy search. You can a greedy search would be a beam search if we changed one parameter in the beam search. So let's say we've got all these words. When we start our sentence with Cambridge, there is a 40% chance the next word is university, a 30% chance it's hummus. If it's university, there's a 30% chance it's press, etc., so on. If we did a greedy search, we would start at Cambridge. We would then see, oh, the highest probabilities with university, I'll choose university. Then the highest probability is press. So you'll end up with the phrase Cambridge University press. Whereas if you did a beam search, and let's say your beam width is 2, you would pick the two highest probabilities. In this case, you have to pick both of them. You look at university and hummus. Then for each one, you would look at the most likely next 2 words. So from hummus, it could be society or selection. And then from university, there's only one word, it's news. From these, you will pick the two largest numbers. So from here, you'd pick Cambridge Hummus Society, that sums to 0.8, or you'd pick Cambridge University News, that sums to 0.7. I didn't realize I changed the word. Anyway, you'd end up with a phrase either Cambridge University Press, or you'd end up with the two phrases here, and you'd realize the highest score, in the end, you'd see which one is the highest valued, and you'd say, oh, it's Cambridge Hummus Society. That's the phrase that was more likely than the Cambridge University Press phrase in your situation. This is especially useful if you're doing something like predictive text on your phone, because instead of just recommending one word that should follow, you can say, these were the 3 most probable words. You probably intend to choose one of them. And your beam width doesn't have to be 3. If your beam width was 1, you would end up with a greedy search. If your beam width was 10, it would take longer, but you'd end up with a solution closer to the optimal solution, etc. So that's how the decoding works. It's a lot simpler than the encoding. That is one point where I'd like to say, are there any questions? Does anybody have any questions they'd like to ask? I can't see the chat because I'm going to PowerPoint at this. So if there are any questions on the chat, tell me, or just turn on your mic and ask any questions.
Yeah, Parth, do you want to ask a question?
Yeah, so are these the probabilities, the 0.4, 0.3 and all? So if they are, then would they stack additively or multiplicatively?
They also, you'd use conditional probabilities. I have just used this as a arbitrary example. These are just numbers that I'm adding as a concept, but usually you do conditional probabilities. So if I had the word university, how likely would press be next? And they wouldn't stack additively. No. Yeah. Are there any other questions? Sorry, I should have explained that a lot of my models, this was just me explaining how a greedy algorithm would work. If there are no questions, I'll move on to the next part, which increases the complexity a little. So let's say we have this sentence. She sat on the bridge and played bridge with her friends. So she sat on the bridge, as in bridge, the game, and she played bridge, like played with bridges. No, clearly not. That's just not what we were intending to say. However, for a model trained, such as a model like word2vec or a model like glove that was trained without any context, those two words mean exactly the same thing. So our pre-trained model has the same embeddings for both of those words. So now we need to consider about adding context. This is an example from a paper. Oh, ELMo will come and help us out in this one, by the way. But this is an example from a paper that introduced ELMo. And in this, we can see the word play in an embedding called glove that does what we did initially. It uses a recurrent neural network to train itself on a large corpus of text and to find relationships between words, and then say, okay, the word bridge regularly occurs next to scenery and nature in games, so they should be near each other in the embedding. ELMo, on the other hand, also adds context. So the word play, as in a theatrical sense, would be very different to the word play as in a sporting sense. Would be very different to the word play as in press play on the TV. Yes, and we need to find out how it added this context. The way you and I would add context is we would look at the whole sentence, remember what was said before, think about what is said later on, and then mix them together. We essentially use memory. So can we add memory to our program? Yes, we can. There's this concept of long short-term memory. It looks complicated. It looks really unusual. What are all of these things doing? There are 4 main purposes of this long short-term memory unit. That is, we're considering how much should the past matter now? Should we drop this information? Is it useless? Maybe the words were and the. Well, do they really matter in this context? Is it really useful? Or should we not bother remembering them? Should we erase a whole cell or not? Does this whole cell matter? Does this entire input matter? And how much of the cell matters for what's coming up next? The way it does this is beautifully described in the paper that I'll mention. However, it was initially designed to solve the vanishing gradient problem or the exploding gradient problem. This would occur because, and I'll show some maths, they're common issues with several neural networks, and they stop the model from effectively training. If your gradients are really low, an incredibly large change in the input still didn't seem to make a great deal of change to the output. Your model is now stuck. So how does LSTM change that? If we look at these equations, these are the equations mentioned in this paper that introduce the concept of long short-term memory and why ELMo used them. And what really matters is this omega t prime minus t term, that there's exclamation marks below. That term, if omega is anything other than 1 on that term, that will change rapidly in either an exploding direction if omega is greater than 1, or it would decrease rapidly towards nothingness if it's less than 1, because of these gamma functions, the big pi's. Whereas this is not the case in LSTM. The maths is described in great detail in the paper. However, the concept itself doesn't require much maths to think of it. It's just thinking there is now some addition going on in my network that negates the effect of my small gradient. It forgets it if it doesn't need to remember it anymore. But there are other alternatives to this. We can also add something called an attention layer, and this is all going to be based on a paper called Attention is All You Need, and also on the concept of BERT, that is bidirectional encoder representations from transformers. This is where we introduce a transformer. It's not the same. It's not. They're not making a pun again. They're not transformers as in the cartoon characters. This is the system. In this system, we have these. You see these things called multi-head attentions. Everything else, a feed-forward neural network we explained before. A softmax is just a function that is it's almost like a rectifier function. It's something you could Google and find a formula for. But this concept of attention is key, because now we're considering, we're paying attention to other things. We're deciding over multiple inputs. We can make this parallel. We can do this on multiple computers. It's not like our recurring neural network before, where it was all sequential and we couldn't do this over multiple computers. Now we're getting computationally better at doing this because we can use attention to consider many different words and think, how much attention do I need to pay to this word? How much does this word matter in the context? And we can get a better output. So that is another pausing point. I honestly don't know how long I've been talking for. But at this point, are there any questions? And BERT and ELMo are confusing, so I am expecting questions. But if you don't have any questions, everyone is just better at maths than I expect.
So can you just explain again, how do you determine where you pay more attention to and where you pay less attention to? Where does this decision happen?
So this decision happens in this multi-head attention layer thing. Oh, you can't see my mouse. Okay, so we take our input embeddings and we split our word by the position in the word. In fact, BERT splits it quite well. The way BERT is trained, it takes 2 sentences and it masks random words within them, and then it sees what word would it have been and it learns based on that. So it sees the position a word is in, and then based on that, it thinks, if I paid this much attention to this part of the sentence, or this much attention to that part of the sentence, what would my weights be? What would my loss function be, essentially? How would it look like at the end? And then it keeps changing how much it is paying attention to different parts of a word and different words. It depends on your context. So the thing, as we mentioned earlier, you've got a context thing to consider, and then it considers my position in the word. And then it decides how much attention to pay. There's that paper that explains it well. And also another thing on the Stanford website, I'll also send the link to that shows it more visually. So you could think of a sentence, let's say there are 2 sentences. One sentence is, my calculator is broken, why would that happen now? I might be saying this before an exam and my focus is on the word now. I'm worried about it happening now. The issue is time. And my sentence before, the fact that my calculator is broken would lead you to think, I'm worried about it being broken now. The issue is that I need to use it. That's what I want to do, and that's why my focus on the word now. Instead, if I said, I just bought a new calculator, why is it broken now? My question is that I don't need it to work urgently, but I've just bought the calculator, why is it broken? Similarly, the attention will consider the sentences that come before, the sentences that come after, and then think, is this word something that the person would want to consider or not? That makes sense. How about you?
So is it kind of by matching to template on the like sense and structure, is that you
Yes.
kind of guess what's okay?
Yes.
Yeah, it is.
Entirely machine. I mean, machine learning is just guessing. It is.
Yeah.
It's guessed many times before, and it's realized this is usually what works, and that's why you need to then fine tune it. But you need to fine tune. It's something that you'll almost definitely need to fine tune to your model later on once you've done all these embeddings.
Mm-hmm.
In fact, before I move on, one other thing that BERT does really well. You might think now that we've added context, we need a lot more vocabulary. We need to store a lot more words, which is true. ELMo does need to store a lot more. But BERT doesn't just consider whole words. A word such as embedding would become embedding. And then it would know the difference between the bed in my word embedding and the bed as in a bed that you sleep on by the way it tokenizes it. It makes tokens out of words. When it takes the words, it tokenizes it, and then it decides where its embedding should go. I don't know why I haven't added that to my PowerPoint, but that's an important thing. It makes BERT reduce the vocabulary it needs by quite some margin, because otherwise it would take way too long to learn all the context for every word. Yeah, that's another thing. Sorry, are there any other questions?
How, if you've got like this many words, you've got such a big bank, how do you know that BERT and ELMo are making the right decisions when it comes to the words and they're not? Like, how do you check for errors and stuff?
So one of the big ways of checking for errors is by doing the benchmark tests. The benchmark data sets are made on several existing problems. So you've got, as I mentioned before, you could check the semantic textual similarity. That is Paris to France what Tokyo is to Japan still, or is it now producing something completely off? That is one big way to see whether or not it works. Usually, so when they first made this, they didn't set out expecting these similarities to exist. They just wanted to encode words in some way and found that when they encoded it, the relationships between words were preserved. So that's one way of checking for it. You'd then check semantic similarity. You would see if it can detect nonsense, can it detect garbage from what isn't garbage. That's one of the best ways. The benchmark tests are what will distinguish a model that you and I will talk about and a model that someone tried to research and it didn't get very far. That's the big way to check for errors. If that answers your question.
Yep.
Yeah. Is there anything else? No. Okay. So now I'm gonna do a quick demonstration, which is very quick. I'm just going to Google. I'm going to go here and just search for, let's say, Cambridge University Mathematical Society. Let's search for it. It's given me the Archimedeans first. It hasn't given me this first, where the title matters exactly. How has it done this? Well, in new context. Google is what released BERT, and Google knows about context. Google looked at it and thought, okay, there is no way she searched for this to want to know about what Kusu has to say about the Cambridge University Mathematical Society. She's much more likely to have searched for it to know about the Archimedeans. There are other things. There's graph analytics, there's PageRank, which is a whole different topic altogether, nothing to do with machine learning. But that's how all the search algorithms that you and I use work. They use context. They read what we said and think, what could the user be wanting to do when they were searching this? And then they display it. And that's That's the big demo. Every time you're wondering how natural language processing works, try Googling something or try searching something on Facebook. This is exactly what they use. BERT and variations on BERT is what they use. So the next part I'd like to talk about is how if you start with garbage and you put it in a state-of-the-art model, these models are called state-of-the-art. What do you think you'll end up with? I'd like to answer that for you. I'd like to say you'd end up with more garbage. It is, if you take away anything from this talk, let it be that all these models, all this maths I'm showing, only works if the data is good enough. I can't stress enough, if you tell a model, I'm going to look at it now, in fact, if you look at a model with biases, you will get biased outputs. Just because a machine is learning it doesn't mean a machine will get rid of all the biases that existed in your data. For example, we're going to look at two CVs of Sporty Nikita and Foodie Nikita. Let's say I'm applying for a data science job. My CV has that I work in Python, I work in C++, my experience is I try really, really hard with my degree. The only difference between these two CVs is that in one, my hobbies are racing and sports and tennis, and the other, my hobbies are eating and watching a show. They could be different. They could be, for example, I might have a hobby that I like to go outside and work in a social care setting. That would be a world-friendly Nikita. But if these two things went through a machine learning model, you would find that Sporty Nikita would be said to be a better programmer than Foodie Nikita. Because when these embeddings were made, the data was made on existing corpuses, that is, existing corpuses with gender-biased data. It's usually said that if you're racing, you're more likely to be a male for whatever reason. The data would often say things such as sports are more close related to a male, and the bias here, even though I've removed all gender, there's no sign of what gender it is. It's Nikita nonetheless. But in the bias data that our machine has learned, a male is closer to programmer than a female. So because racing is closer to male than a female, me having racing on my CV now makes me more likely to be employed for a job where nothing is different between me and Foodie Nikita. I mean, maybe you could argue playing Mario Kart is more useful than watching the Bake Off, but nonetheless, there should be no reason why there's bias. You could even remove the names. You could say Sporty CV, Foodie CV. Those words, sporty and foodie in themselves, would lead to a bias. So one of the most important issues that we learn to face in these models is that biases would inherently exist. And instead of saying, oh, I will feed my network with absolutely unbiased data, we should work to remove these biases. I will quickly explain a way to remove these biases in the next slide. But before that, I will also explain another issue that the models face, and that is attacks. I put a question mark because this will then link to the biases earlier. But attacks are a big issue with machine learning models. That is, look at this image. Let me ask, Kamath, you're here, you can turn your mic on. Tell me what that is. What do you see in that image?
It's a cute fluffy panda.
A cute fluffy panda. What do you see in this image?
The same panda again?
The same panda again. And what do you see here?
Just some noise.
Yeah, perfect. That's, unfortunately, you're wrong according to the model, because you were right with cute fluffy panda. The noise it recognized as a random animal is very low confidence, but unfortunately you were wrong. The second panda wasn't a cute fluffy panda. According to our model, it was a gibbon. So this is the example of an adversarial attack. We have added essentially noise to an image, and to you and I, it looks exactly the same. Why does it look like this? But to our model, it's entirely different. This is discussed in a paper by a man called Ian Goodfellow, and he then explains how you can actually cause these attacks yourself. For example, let's take these images. I'll ask someone else. Maybe I'll ask Yuri. What do you see in these images?
Well, there's a stop sign, and the stop sign with some rectangles. They're probably like some stickers glued on top of it.
Okay, so this is something that you could expect to happen on a normal road, right? People can glue stickers onto a stop sign. Now imagine you're going in your automated vehicle. It's learned on some machine learning algorithm, but it's a very naive machine learning algorithm. It hasn't been exposed to the possibility of attacks, or maybe someone has told everyone the loss function of your algorithm, and they can now do an adversarial attack on it. And now instead it sees this. Once again, Yuri, what do you see here?
Well, a speed limit, 45.
Yeah, 45-mile speed limit. Very different to a stop sign, but to your model, they're the same picture. This is actually explained in the paper I've linked over here. This is actually what a model saw, and with sometimes random, usually intentional perturbations added to original image, it can entirely change what your model sees. And these are adversarial attacks. But you might be wondering why I'm showing you images. I came here to do a talk on natural language processing. Why does it matter? It kind of does matter. If you look at this method, the fast gradient sine method, this is a method that Goodfellow described to cause an adversarial attack. It uses this beautiful equation. Now, let's say we've got a filter that filters emails as either spam or not spam. X is the output value it has. It's a one-dimensional graph. If your value is more than 0.5, you're spam. If your value is less than 0.5, you're not spam. Let's say you begin with X at some value and you have a loss function. A loss function is essentially how much it is costing your algorithm to have those weights. If your algorithm was being punished for being incorrect, it is how much it's being punished for being incorrect. And this is your gradient of your loss function, the direction in which it's changing. You want to pick the sign, you want to go in the direction to maximize your loss function, and you have a little epsilon here. Let me explain what each variable means here. So X is some input. You cause a perturbation to it, like here, they cause some perturbation to it, and you end up with an adversarial output. Now, instead of your spam emails being marked as spam, you have somehow learned to add a slight change to it so that instead it marks them as not spam. This is a big issue with text. You could say, okay, fine, they might just be adding random letters. That might not work so well. But if somebody knows your loss function, if for whatever reason your company's secret was leaked, they could then cause however many adversarial attacks as they wanted. They could always make their spam email appear as though it's not spam, and it would always be an issue for people. There are ways around this. The biggest way to sort this out is to not expose your loss function to anyone, because essentially, if they don't know this, making the adversarial output becomes a lot harder. Now, instead, they have to keep probing your model. They have to keep sending emails and seeing what does and doesn't come up as spam. And then they have to decide, okay, given these outputs, I think their model looks like this, and they have to guess too much. But if they don't have to guess, they can easily send you more and more spam emails for no reason. So that's the adversarial attack issue. I wonder if, yeah, so this is the TensorFlow. It's on the TensorFlow website. TensorFlow is a tool, it's a framework that you can use to do machine learning in, but it explains and gives a tutorial in this method really well for images. But this also then gives us an idea for, let's go all the way back to our issue with biases. How about we try this? How about we take our embeddings? We've done all this hard work of encoding using whichever encoder we liked, and we consider for our purpose, let's say we're analyzing CVs, and we want to get rid of any gendered bias, get rid of any racial bias, any bias linked to age and disabilities, etc. We might then think, what words are gendered, or what words would link to these biases? You've removed all the explicit words, you've removed their gender, you've removed their name, but there are still proxies, such as the gender divide between what hobbies people like to do. We can take these words and we can perturb them a little. We can find a line, let's say there is girl and boy, and there is a line between them. We can find a perpendicular bisector of this line, essentially, and we can move all our gendered words so they lie somewhere on that bisector line. So now the distance from each gender is the same, and they're no longer gendered words, meaning it's a lot less likely that your model will bias based on those words. There are also other issues that can be caused. I mean, maybe your data is just not trained on enough things, but certain things like the word encoding on a huge corpus, the glove is embedded on Twitter, BERT is embedded on things like Wikipedia, huge book text corpuses. It's unlikely that there are things they haven't come across before that will cause bias because you don't have enough data, and you've now tried to remove biases by using a technique that you thought was only possible to attack in, and you've now got a much better, a much less biased network. So that is pretty much all I have to talk about. That is a whistle-stop tour of everything that can be done with natural language processing, and everything that needs to be done in the future. Are there any questions now linked to any of what I've just discussed? Oh, everyone happened to know quite well. Okay, so I hope you've all gained some insight from this presentation. That is kind of the maths that goes behind it. Essentially, a lot of it is just linear algebra, some differential equations thrown in there. The mathematical part isn't what distinguishes each model from it greatly. Surprisingly, the mathematics does distinguish each model greatly. I shouldn't say that, but little changes in the function don't create drastic differences. It is entire changes in concepts. It's things such as considering the attention layer and the transformer layer instead of trying to somehow just move an RNN across many computers that made that leap from something that you can train only sequentially to something which you can train across parallel computing. One of the big things that we have to consider is these things take a lot of computational power to originally train them. You and I can use a pre-trained version of BERT, but somebody has had to sit there training BERT on hundreds of millions of words. And to be able to parallel compute is something that is increasingly in demand right now. That might be something people want to consider. One of the big things for me is removing biases and protecting against adversarial attacks, especially things like what they call white box attacks. That is where I know your loss function. I'm obviously always here to answer any questions that you might have on natural language processing, on any of these concepts. I will link to all the papers if you want more in-depth of exactly what happened in each equation. But if that's it, then that's all there is from me.
So there's a couple questions in the chat now.
Okay.
So firstly, yeah, Sean's asking, what actually happens with the vectors? So you showed how we convert the words into vectors, and how do we convert them back?
Yes, so when we start with the vectors, we then consider our use case. Let's say our use case is predictive text. We've got all these vectors. We will consider the cosine similarity between the vectors. That is how near two vectors are to each other, and use that to predict. And we will also consider, so context and things will come in later, but if you remember quite early on when phones had predictive text, you could make really nonsensical sentences because it would just tell you the next word, the next word, the nearest word, the nearest word. That's when all the embeddings were just a embedding, a bunch of vectors, and it would tell you the nearest word is this. So clearly the person wants to use this word. Clearly the person wants to use that word. It wouldn't consider how a sentence might follow beforehand. But yes, you would then see how similar they are. Then you would make your probabilities. You would go towards the you would go to the greedy search algorithm or your beam search algorithm. There are other search algorithms as well. Beam search is usually the best one. There are also improvements on beam search just because it takes you to a more optimal solution than a greedy search, but it doesn't take as much time or complexity as the most optimal set of vectors would be. So that is how you would go back from your vector to a text. Hopefully that answers your question. Please, I'll check the chat. In fact, I will stop sharing my screen and check the chat if there are any other questions. So what else do we have? How do you think you could explain the removal of bias to non-experts? So the removal of bias, I feel like it's, for me, the best way of describing is you're essentially taking a set of words, doing your best to make them non-gendered. You're saying, if I was a common words, for example, the word child. Child, for whatever reason, comes closer to female than to male. This will be biased against someone that might want to go into childcare and they are a male or they're not a female, and they might then feel that, oh, well, for whatever reason, our machine learning model believes this female here is more likely to do it than you because of her gender. If you then moved it so it was the same distance from both words, your machine learning model wouldn't make that distinction. It would then look at other things that are non-gendered factors. You also have to move it from use case to use case. Close in meaning nearness in vector space. Sorry, I'll finish the other question first. Yeah, so you'd essentially want to make the words that matter to your use case non-gendered. Certain words such as programming being closer to other programming languages, you don't want to move those. You only want to move your gendered words. Also, nearness in vector space. Nearness in vector space means close in meaning. Nearness in vector space would mean that's what I showed earlier with they run these benchmark tests that will take the similarity between them, and it will then tell you that, oh, king and royal are near each other. This is another test they do. They test if words that should be similar are similar in benchmark tests. They're not appearing often nearby in sentences. Appearing often nearby in sentences is more linked to your attentions and your context. That is how they're positionally embedded. Usually a vector space embedding would be they're near. How often are these algorithms used in the hiring process? I've been working in a data science company for my Easter holiday, etc. And we were discussing between us, and myself and a few of my colleagues are in a pretty high consensus that most big companies you apply to will use these NLP algorithms to sort through hundreds of applications. It's very unlikely that every single application is read by a human. There are services that are provided to other companies that they can buy into to help their CV extraction. The HR doesn't have the time or the resources to go through every single application. Usually they will put all the applications through an NLP model, and it will give many of them. So let's say that it wants just the top 100 for a human to read. So yeah, they're used in quite a few hiring processes, I'd say. I'd actually like to mention, there are some cases when this could go wrong. If you want to, let's say, consider, I believe there's a case when there was a service that would do video interviews, and it would look at the movements of people to decide how are they more likely to be enthusiastic. They might be saying something, but the way they're moving their hands or the way they're moving their face, their expressions might decide whether they're more or less enthusiastic. This proved problematic because the data put into it was actually biased data. It was more Caucasian data than data of people of color. So it would automatically assume a person of color is worse because it's good data. What it considers to be good is Caucasian because of the data that's been input into it. Okay, now another question. How do you recognize bias? As in, an algorithm selects men more often than women. How do you know exactly where the bias is? So recognition of bias, I believe people have just analyzed what an algorithm is doing over time and noticed that this algorithm is more prone to hiring men than women. Why? Also, you can work backwards and think it chose this person. You can work backwards and think why it chose this person, because this word gave it a higher score. And then you realize that word was actually a proxy that caused this higher score. But it's also context dependent. Maybe your context isn't sensitive to it. Maybe your context doesn't require consideration of gender bias. Maybe your context is you're trying to see within a certain number of, let's say, children, you're trying to see, is there a link between their gender and what book they're studying to read? Maybe in that case, you don't want to get rid of the gendered words because you're trying to analyze bias as it is. But it all depends on your use case. That's what I mean by embeddings. The context doesn't matter with embeddings. Context doesn't matter. With embeddings, you need to then fine-tune it to your use case. You're using a pre-trained model. You can't use it pre-packaged for you. You have to then suit it for your own needs later on. Hopefully that's Shavindra's question. Are there any more questions? Someone. That is exactly the meme. That is exactly the meme I was thinking of when I thought of the other one, the one where it shows a stop sign, it doesn't see a stop sign, but it thinks they're the same picture. Yes, that is all I'd like to explain. If there's any other questions you have, you can.
Oh, actually, can I ask another one?
Yeah.
So you said that the closeness in the vector space is like semantic closeness, kind of, right, rather than being closed in a sentence. Then how do you train this data? Because you can't just give it loads of text. You have to explain to it when words are similar, and how to explain to it like millions of words.
So this all links to when you train the model. When you're training it, you are training it, at least the way BERT works, the way a lot of things works, not a lot of algorithms work, is they see many words. I'll explain a much simpler case. I'll explain word2vec, one of the initial things that came out in 2012. Word2vec had a window size. It took a word, it had a window of, let's say, 2 words. So if my word is they are not the same picture, that's my sentence. Then it would have a window of 2, and it would look at the pair of they are. It would look at are the, they the. It would then look at the same, the picture. So it is looked at words that are next to it and another word next to it, 2 up to the window of 2 on either side. And from there it has figured out, okay, usually these 2 words appear together. Usually when someone says horseback riding, somewhere within that sentence or within the next couple sentences, they're likely to mention a saddle. They're likely to mention a horseshoe. And that is how it has decided they must be semantically close. We haven't told it. It's usually unsupervised. At the very start, at least. You get a bit more complex when you get to things like BERT, but it begins unsupervised. You're just given it a bunch of data and thought, okay, computer, what words do you think are similar? Or maybe it might say, this word always follows the. These words always follow the. It has itself guessed that they must all be the same category of words. We would call them usually nouns or adjectives. It's unlikely that there will be verbs. You can have verbs, but it's more likely there'll be a noun or an adjective. And the computer has figured it out itself. And also, I'd like to say, these vector embeddings are several dimensions. They're not just 2-dimensional vectors. So you could have several dimensions for each little feature it has extracted. It is, in some ways, it's very different, but in some ways, it is no different from you trying to extract features from an image, right? You have to consider several features. You're not just considering, oh, in this 2-dimensional graph, king is close to queen. Well, where does every other word go? Where does song go? Surely songs would be close to queen, because maybe I'm talking about Queen the band, not Queen the queen. And things like that. Hopefully that's a reasonable answer.
Mm-hmm. Okay, so, and then I guess does it use transitivity kind of to find closeness? So, for example, if you have 2 synonyms, right, they probably wouldn't be used next to each other because you just choose one of them or the other, but then they're used next to the same words. So it's like if they're both used in the same situation, then you say that they're close.
Yes, that's why the so this links me to the fact that how much data you train it on makes a huge difference. But there's a BERT base and a BERT large. BERT large is trained on about twice as much data, and it has significant improvements over BERT base. BERT base isn't small. BERT base, I think, is 140 million words. It hasn't come across few words. But the more data you make it encounter, the better these embeddings will be, because as you said, it will start noticing that me saying the word sunshine and sun rays usually occur in the same context, so maybe they're very similar words. But if it hasn't come across those contexts before, there'll be an issue. There's also something that some people might like to go away and research, which is how do you handle out of the vocabulary words? What if I come across, before the word swag was popular on the internet, if my machine learning model came across the word swag, what would it do? Well, how would it know how to react? And that's when embeddings, that's when you can come up with subword embeddings. I guess that was a very bad example. There must be better examples where you can break up words and find that your subword has a definition and that helps you infer the meaning of another word, if that makes sense. Yeah, so like if I'm saying calculator and calculation, the word calc can be used in both contexts. You know, then if somebody comes up to you in a different language and says calculatora, you know kind of where it should be semantically. Yeah, so that is
Okay, thanks.
everything from me.
Great. Yeah, if there aren't any questions, yeah, let's thank Nikita. This was really interesting. Nice to see something very applied about how this is actually used. So yeah, thank you.